Welcome back, everyone. This is 2C. It's extra practice. I'm going to go ahead and go through it. Anyways, this is all about different problem-solving techniques, how to think outside the box, about how to solve these problems, and some interesting examples that are here. Some of them might really help you if you draw a picture. Actually, a lot of them. I tell you that if you want to see these problems worked out, almost all of them are very, very, very close to the examples that are in the textbook for section 2C. And I would highly recommend that you go there and look at those problems and the explanations that are there. There's two different ways to approach problem number one. One of them is to approach it quantitatively and actually figure out each runner's speed, and because it says they run at the same pace, which is their speed, and set up the second problem and figure out at that speed how long it would take them to finish the race and which one finishes first. But there's a more intuitive method here, which is that in situation one, and I think I can draw off here, no, I can't draw on the margin. So I'll just draw up here and then I'll erase it. Situation one, Saul and Paul start together, and Paul finishes all 50 meters in the same time that Saul only runs 48 meters. Okay, now I'm going to change color here, and in situation two, we're going to make Paul get moved back a little bit, and Saul stays there. Now, this distance right here is the same 2 meters that's right there, okay? So if I just move Paul back 2 meters, then his spot he would finish in the same amount of time is right there at the same spot that Saul got to 48 meters. They both get to 48 meters at the same amount of time, but that's not where the race ends. The race ends down here. Paul clearly ran faster than Saul, finished faster here. So Paul is going to get to the finish line faster than Saul would. I don't care exactly what this distance is in between them. The problem doesn't ask me, it just asks me who is going to finish the race first. And the answer to that intuitively, and if you did it quantitatively, is that Paul is going to finish first place both times, that moving him back the difference of 2 meters here is not going to change his winning the race. You're going to have to move him back even further if you want to try and get Paul and Saul to cross the finish line at the same time. All right, this one's tricky because you want to focus on the thing running back and forth, or in the book, it's a bird that's flying back and forth between two cars. So you've got two bicyclists, we'll call them A and B, and you've got the greyhound that I'm going to call G. Spot is going to be running back and forth between them. But the thing is that A and B are closing on each other. So as soon as G leaves A, B is approaching him, and then he gets to B wherever he gets to him and turns around and starts approaching A, but A is approaching him and is no longer where he started. And so if you focus on the Greyhound here, it's like, wow, that's a really complicated problem. I'm going to tell you there's absolutely no way to do that problem with the math that you know. That would require calculus. Okay, it would do lots of stuff with the rates of change, which is what calculus is. Instead, let's forget about the Greyhound for just a second. Let's pretend he's not in the problem. Let's go back to Algebra 1, where we had two trains that are approaching one another, or two cars approaching one another, or two bicycles approaching one another, right? Here, and the distance here between A and B is 42 miles. And one cyclist is traveling at 15 miles per hour, and the other one is going at 20 miles per hour. So you know if they're coming towards one another, that's a closure rate of, and I would add these two numbers together, of 35 miles per hour. So I need to think, how long does it take them to close the 42 miles? Well, dirt, distance is equal to rate times time. So D over R is equal to T. So 42 miles divided by 35 miles per hour is going to give me 1.2 hours. Now, what's important here is that Spot's velocity never changes, that he's running at a constant 38 miles per hour, that somehow he's able to instantly turn around and go the other way and never lose any speed. Okay, so if he's running 38 miles an hour the whole time, back and forth and back and forth, he's doing it for the whole time until they, get to one another. So I just need to multiply his velocity, his rate, times his time, which is going to be the same time, to find the distance that he traveled. And that's going to give me 38 times 1.2 is going to be 45.6 miles he's going to run. Okay, so it's a hard one, right? Now they give you a different problem here for 3 in the book, and they tell you to think of it as red and yellow marbles instead. They're actually going to give you the red and yellow marbles here, but the problem in the book starts off with different colors of paint. And you're pouring from, one kind of paint into the other color of paint, and then pouring the mixture back into the original. Or, you could start off with fresh water and salt water if you wanted to, something like that, and pour some salt water into the fresh water, and then pour the brackish water back into the salt water, whatever you want to do like that. And so this idea here, draw a picture for yourself if you need to, but they explain this really well in the book with pictures, that you have a red bucket containing 12 red marbles. So imagine this is like the red paint that we were talking about in a yellow bucket with 12 yellow marbles. You have the same amount of paint or same amount of marbles, in each bucket here. So they're representing red paint with red marbles and yellow paint with the yellow marbles, let's say. Mix them together, you'd get orange paint, but we're not going to do that. We're just going to look at, because we don't want to see the mixture, as a new color, we want to see the red and the yellow parts here. So we're gonna look at marbles that won't mix together, right? So you remove 3 marbles from the red bucket and put them in the yellow bucket. So 2 buckets, and you originally started off with 12 red, 12 yellow, and you're gonna take out 3 red, leaves me with 9 red, and I'm gonna put the 3 red over here. Okay, now it says that I'm going to take any 4 marbles that I want from the yellow bucket and move them to the red bucket. So I could move all 4 of them as yellow, right? Or I could move 3 yellow and a red, or 2 yellow and 2 red, or 3 yellow and 1 red. I can't move 4 red though, right? So I'm going to, it's asking me the number of yellow marbles in the red bucket. So the most yellow that I could put in the red bucket, since that's what I'm interested in would be to move 3 yellows over here and put 1 red back, and take 9 yellow and 2 red, right? So now the question is, are there more yellow marbles in the yellow bucket or more red marbles in the red bucket? So, and if I did this, there should always be 1 more red marble in the red bucket than there is yellow marbles in the yellow bucket, no matter which way I do that. I could prove that to you very generically, or I could show you all the cases, but there's always going to be 1 more red marble here than there is yellow marble here. So there's going to be, let's see, which is greater, the number of yellow marbles in the red bucket or the number of red marbles in the yellow bucket. I think I said that backwards, but take a look here, that there's always going to be 1 more red in the yellow than there is yellow in the red. That's what I meant to say. So I just kind of looked at it backwards, but there's always going to be more red in yellow bucket. And again, we could show that to you generically, but draw out pictures for each situation if you need to. There's like 4 total ways you could end up based off of if you pulled out 3 yellow and 1 red, or 2 yellow and 2 red, or 1 yellow and 3 red, or 4 yellow and 0 red. You can check all those situations and see in every single one there's going to be more red marbles in the yellow bucket than there's going to be yellow marbles in the red bucket. All right, turns of wire wrapped around the pipe. So they're going to show this to you and say, all right, you've got something cylindrical. The easiest way for you to do this problem is for you to actually think of cutting the pipe open into a rectangle, and that each of the turns of wire it's got 8 turns of wire, so every 1/8 of the length here. So you've got 1, 2, 3, 4, 5, 6, 7. See, I'm not good at drawing this. 8, like that. Imagine those are all equally spaced here. And then imagine that, these make diagonals of rectangles that are here, right? So these are diagonals of rectangles that get made here. And then this one's a diagonal of another rectangle that gets made, and that there's 8 diagonals of 8 rectangles. So you can imagine that. Let me try and draw the representative rectangles here, because that's really what I just need to show you, is that each rectangle that I have is going to be a width of, the width is going to be the circumference here is going to be 4 inches of circumference, and then we need 60 divided by 8 is going to be 60 divided by 8 is going to be 7.5. And I want to find, Pythagorean theorem. I want to find this side of the rectangle. So that's going to be 7.5 squared plus 4 squared is going to be 72.25. For that's going to be that side squared. So I need to take the square root of that, because a squared plus b squared equals c squared. So square root of 72.25 is 8.5. So each turn of wire is going to be 8.5 inches. I've got 8 of those turns of wire. So 8.5 times 8, I should have 68 inches of wire. Okay, there's a few different problems like that, but sometimes take something 3-dimensional, cut it open and lay it flat to make it 2-dimensional, and it's actually easier to work with, especially when you can see what the turn of wire is and that it's this diagonal on this rectangle. All right, suppose that China's population policy is modified so that every family can have children until either a boy is born or 2 children are born, whichever comes first, assuming every family chooses to have as many children as possible under this policy, and that boys and girls are equally likely. How many children would be born? Typical group of 1,000 families. Well, there's a 50% chance that they get the first child as a boy and then they stop. There's a 50% chance that the first child is a girl, right? And then they would be able to keep going. Then from this, there's a 50% chance that the second child is a boy, and they'd have to stop. And there's a 50% chance that the second child is a girl, and then they'd have to stop. So 50% of the time they'd have one child that's a boy, 25% of the time they'd have two children, a girl and a boy, and 25% of the time that they've had two children that are two girls, but half of the families are going to have two children, is basically what it comes down to, and half of the families are going to have one child. So there's going to be 500 families with only one child, plus there's going to be 500 families with two children, half and half. 500 plus 1,000 children is going to be, there should be 1,500 children. All right. A curved bridge over a river, so that the two endpoints of the bridge are 140 yards apart horizontally. You walk across the bridge with a device. So you have a bridge that's like this, but these are 140 yards. You find out that this arc, because the bridge is an arc, is actually 142 yards, like this. And so approximately how high is the bridge? Well, we're not going to be able to measure it with curvature like that. In this class, curvature is something that would require calculus. So we're going to imagine, because this diameter and this length are so close to one another that this height is not super, that the difference between this being curved and this being imagined to be triangular in nature is not significant. So I'm going to take half of the distance that's the curvature, and I'm going to call it 71, and take half of this distance, and I'm going to call it 70, and I'm going to say 71 squared minus 70 squared inside of a square root sign is approximately what the height is. So I'm going to figure that out. 71 squared minus 70 squared is 141. I'm going to take the square root of 141. I'm going to say that this is about 11.87 yards. Okay. Similar question, but different. So they're going to give you the height now. So we're going to just go ahead and set up the triangle. They tell us that this is 350 feet. They tell us that the endpoints are 1 mile apart. So I need to change miles to feet. Half of a mile would be half of the bridge. If the bridge is, you know, has a span of a mile, half of that span is going to be half a mile. So this is 5280 divided by 2 is 2640. So this side needs to be 2640 feet. Okay, so then we need to take the square root of 350 squared plus 2,640 squared is going to be roughly 2,663.1 feet. And then it says the walking distance, so I want to double this because that's only half of the distance you'd walk. So this is going to be roughly 5,326.2 feet that you'd walk across the bridge. Suppose that you have 10 white socks and 6 black socks in the clothes dryer. How many socks would you have to pull out without looking? Imagine that you go in there in the dark, can't see to be certain to have a pair of white socks. Well, worst case scenario is you pull out all the black socks first. So we're going to pull out all 6 black socks. Plus we need a pair of white socks. So we'd have to pull out 8 socks total. It's an idea called the pigeonhole principle. It takes you 84 seconds to walk from the ground floor of a building to the 4th floor. How long will it take you to walk from the 1st floor to the 10th floor at the same pace, assuming all floors have the same height? Okay, be careful here because you need to count staircases and not floors. So how many staircases to go from the 1st floor to the 4th floor? You only need to take 3 staircases, right? So 84 seconds divided by 3 staircases, going to be 28 seconds per staircase. Now, how many staircases do you need to go from the 1st floor to the 10th floor? You need to take 9 staircases. So 9 staircases. And this is going to be 28 times 9 is going to be 252 seconds. If you wanted to write that in a way that was probably more meaningful to you, that this would be 4 minutes and 12 seconds, I think. Give me 1 second here. 4 minutes and yes, 4 minutes, 12 seconds. All right. Father and son are in a terrible car accident. Father is killed. The son, badly injured, is brought into the hospital for emergency surgery. Surgeon takes one look at the patient and exclaims, "This is my son." How is this possible? Well, the surgeon is his mother. And that's just a riddle because people have a bias, a preconception lots of times that surgeons are going to be men. And you're like, wait a second, the father is dead. How is this possible? No, you got to think outside the box. The surgeon is his mother. That both the father and the mother get to say, "This is my son," right? Trader bought a stock for $20 and then sold it for $30, so he made $10 there. He bought it back for $38. Don't worry about that part there, about buying it back for $38, and then he sold it again for $48, so he made another $10. How much did he gain or lose in these transactions? He made $20. So don't worry about the fact that he had to buy the stock for 38 that he sold for 30. It's not your problem, right? He came out plus 10 in this part. He came out plus 10 in the second part. So he came out plus 20 overall. It's a large jar of marbles containing red, blue, yellow, black, and white marbles. How many marbles must you draw without looking from the jar to be sure to get at least 3 of one color? So worst case scenario is that you are going to pull 1 of each color for the first 2 draws, and then whatever you draw for your or not first two draws, but your first 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 draws, right? Because there's 5 different colors. So you're going to get 2 full draws of one of each of the 5 colors, and you need one more than that. Whatever color you pick next is going to make 3 of a kind something. So that's going to be 10 plus 1 is you're going to have to pull 11 marbles. Again, that's a worst case scenario problem. If you could go faster than that, but that's the slowest that you can get to 3 of a kind there. All right, this one is tricky. All right, this is a logic problem. I like these kinds of logic problems. I have whole books of logic problems like this. So we've got Abe, Boris, Cal, and David all proposed to Ellie, and they say, A, B, C, D, E. You notice that, so you can just abbreviate A, B, C, D, E if you want to. Abe proposed at 5 o'clock, Boris at 6 o'clock, Cal at 7 o'clock, David at 8 o'clock. Ellie accepted the last of the 4 proposals. Now that seems obvious until they tell you, wait, the times may be AM or PM. So this person could be 5 AM and this could be 6 AM. Holy cow. So this is not as easy as we thought, right? So Boris proposed before A. So B is sometime before A. We'll leave some space in case there's somebody in between. At least one suitor proposed between the proposals of Cal and David. So this is either C and D, C and D, C and D, or it doesn't say that it has to be C first and then D. It could have been D and C, D and C, D and C. So there's somebody between them though. D and C are not next to each other. So that probably tells us that A and B are not next to each other. And it's a good thing that I left some space. Cal did not propose between Boris and Al. Okay, so C is not here, which means C has to be either here or here. So, and it says Cal proposed, now I'm going to have to use the times to figure out where Cal is. Cal's at 7. So let's think of this. If Cal is 7 AM, we have to figure out if Cal is 7 AM or 7 PM. Then that would mean that David is going to have to be, let's see, Boris is going to have to come after him then. So Boris is 6 o'clock. Well, that means that this has to be 6 PM. And then that would mean everybody else would have to be PM because they're going to come after that, right? So then A is 5 o'clock, right? And that's going to be 5. Nope, that doesn't work. It doesn't work for Cal to be up here. So we're going to erase that. That's not the option. And we know Cal can't be in the middle there. So that means Cal has to be the last one down here. We knew that this wasn't C. We knew that this wasn't C because the times wouldn't work out. And from that clue, so all I really care about is that Cal is the last person. Now, if you want to figure out the whole puzzle here, then we can go back. We can see, okay, who's left? D and A, B, C, D. D is left, and D needs to go D can go either here or here. And let's see here. So now let's try and figure out where D goes. B is going to have to be in the morning then, right? So this is going to have to be it's going to have to be 6 a.m. D is this is probably 6 a.m. This is probably 8 a.m. He's not here. This is probably 5 p.m. and C is probably 7 p.m. That's what looks right to me, okay? So this is going to be B, D, A, C. For your order, 6 a.m., 8 a.m., 5 p.m., 7 p.m. The main thing that matters though here is that C, Cal, is the last one to propose to her, and it says that she accepted the last of the 4 proposals. So that's Cal. And we had that figured out before we even placed everybody. All right, that is it for 2C. Again, that was extra practice. So we will come back again soon with the assessment preparation videos for chapter 3. See you guys next time.